welcome. We're about to start our seminar this afternoon, and as we always do, we would like our audience to be aware of the exit signs in case we need to leave on a abrupt, short reason for getting out of the room and possibly the building. For those that are on the internet, we're encouraging folks that are interested in sending emails for the Q&A to send them at your first opportunity. The address is probably right now on the bottom of your monitor. That's sierra.rm@calepa.ca.gov. So with that, Ralph.
Thank you, Peter, and welcome everyone. I'm Ralph Proper, and I've been the contract manager for this research. So therefore, it's my pleasure to introduce Donald Dabdub and Mark Carreras-Sospedra, if you pardon my accent. Donald received his doctorate from Caltech in 1995, working with John Seinfeld. Since then, he's been an engineering professor at UC Irvine, working in its Advanced Power and Energy program. Since it's St. Patrick's Day today, I'll paraphrase Sir Arthur Sullivan by affirming that Dr. Dabdub is the very model of an air pollution modeler. He has studied the impact of various energy-related scenarios on urban airsheds and has improved our understanding of the dynamics of atmospheric aerosols and global climate change. He's been the principal investigator for 6 research projects for the ARB. And today we'll hear about his latest, which is on the potential air pollution impacts from future biogas and biomass projects in California. Most of the work for this project was done by his colleague, Mark. Mark studied landfills and wastewater management in Barcelona before coming to UCI in 2001 to get his master's degree in mechanical engineering. But he met his wife there, so he stayed on to get his PhD, and he's still there working as a project scientist. His work is focused on the air quality implications of future energy scenarios. I've enjoyed working with them very much, and I look forward to their presentation, as I'm sure you are too. Thank you.
Thank you, Ralph. It's a great pleasure to be here today. We have had a really wonderful experience during this project, and I know that the ARB it's very active and very a lot of seminars were going on. So I really want to thank Ralph and Peter for really going out of their way to schedule these events, and it was such a beautiful day compared to Irvine. I could not believe I'm saying this, but the weather in Irvine was very hot, and here it's very pleasant, and it was great to, in the last few hours, see a lot of old friends, old program managers, and some old students. So with that, I'm going to share with you some of the results that we have in this project, which is on the impacts of emissions related to biomass and biogas use in California. This is the outline, and it will be a dual presentation. We have the overview and the first third or so of the presentation. I'll do that. Mark will take the second third, and then with the conclusions, which is the methodology and whatnot, and then I will go and deliver the conclusions, the summary, and also a little bit of potential future work that it's on the work. So let's get started. Let's get started, and this is some of the questions that I think that we wanted to start looking at. What are some of the biomass resources that are available in the States, and how can we use them? And in particular, of particular interest to me is not only this characterization of what and how to use it, but more importantly for my interest is, once you do that, how are they going to affect the air quality and some of the perhaps greenhouse gas impact? So this resource, it can use in a variety of ways. One of them is for biopower and also for fuel. And each of these major branches, it sort of goes into sub-branches. For example, in the transportation field, we have ethanol, CNG, hydrogen, and that could be, potential uses for this. But there are compelling arguments to start looking into the feasibility of biomass and biogas. One of them is the issue of sustainable energy and the reduction of greenhouse gas emissions, and of course the whole overall pollutant. So let me give you first a general methodology that we have in our group, and then we're going to start focusing a little bit in the specifics of the project. So this methodology that we have in our group and we're going to apply here, it's basically a combination of air quality modeling, which is where I started my training and whatnot, but it's a little bit more than that. It combines air quality model with emissions modeling, with a little bit of energy issues, with a little bit of transportation issues. And I like that diversity, and we are able to sort of stay at the boundary where air quality meets energy and transportation. So when we have the flow of project information, sure, it's starting to develop some technology scenarios. In this particular case is biomass and biogas that will eventually feed some type of perturbation to an emission input that goes finally to an air quality model. So yes, there is a lot of air quality, but that's only the last step on a bigger project flow. In particular, to give you some of the details, the tools, the modeling tools that we use for input to these emission perturbations are models like the smoke model that in itself requires some baseline emissions that we can get from here or from NEI or whatnot, and we have to make sure that we use the right emission factors and whatnot that are coupled with this. We have also geographical information system, yet another modeling tool that works with emissions modeling tool and sometimes we have to develop our own models when we talk about hydrogen, for example, in other projects, distribution and whatnot, that those are homemade tools that are project specific that needs to be required. And finally, we are able to sort of generate the input to start doing the air quality. And in our group, we have the capability to run model like CIMAC, model like CAMEX, the model that we have been developing that we call the UCI CIT model that started with my doctoral work at Caltech with John Seinfeld, but that has been evolving constantly for the last 20 years or so. So we call that the UCI CIT model, or some of the other models that we have that are sort of different scales and whatnot. And of course, for that, we need the meteorological fields, and that requires yet another model, things like WRF-Chem. So at the end of the day, you see a combination, hopefully working together, of air quality models, meteorological models, emissions model, geographical information system that are coupled in the right way to answer some of the questions that we may have. And then you do see some of the results in whether it is ozone concentrations or NOx or PM and so on and so forth. So that's the overall flow. In particular, for this project, we have the technology scenarios to use are different scenarios related to biomass. These scenarios could be the business as usual. It could be getting the industrial boilers as we have done, or it could be maybe some technology upgrades, and we're going to talk about all these different biomass scenarios that we develop, and then take the scenario that was developed and determine what the emissions inventory as a function of space and time result associated with that inventory is, feed it to the air quality models and do the computations there to be able to determine everything such as NOx, particulate matter, ozone that comes with that, and we also might get some. We also get some greenhouse benefit, and then you might say, oh, this is what happens. I wonder if instead of these scenarios, I do something else. So you sort of close the loops and you develop a different scenario that want to be studied. In particular, I like this project quite a bit because it has a lot of ties to policy and research. To this audience, I'm sure that there's somebody here who is a far better expert in these things, but I will very quickly mention a few of these policy ties that happens. For example, AB 32, in which we have to go back to 1990 levels by 2020. And if we look at the follow-up of that, which is the Governor's Executive Order S305, if I remember correctly, that by 2050, it's not only 1990 levels, but it is 80% further reductions in GHG emissions. And then we have SBX12, which is the renewable portfolio standard, which basically say that the utilities, 33% of the electricity that is has to be met by renewables. Today we are 20%. So the AB 1900, which is the standards for the health protection of biomethane, AB 118, which is basically the technology for cleaner technology and support for that. AB 341, the mandatory commercial recycling, 75% of all the solid waste is made by commercial, and then the AB 341 indicate that 75% of that solid waste has to be recycled by 2020, and a few other more efforts and whatnot, such as Governor Brown's going towards 20 gigawatts of sources of energy coming from renewables. That is all renewables, not only biomass, biogas, but if we look at that historically, it has been about 20%. So that means, on the order of 4 gigawatts, and that seems to make sense with the numbers that we have. And then ARB's own effort, whether it's the low carbon fuel standard, which is 10% of the carbon impact of the fuels, the integrated energy policy report. This is by our sister agency, the CRC, that every year or two, more recently, they put this report that describes all the everything related to energy, where the energy comes from, how it's distributed, what are the sources and demands and whatnot, and finally the ARB initiative about sustainable freight transfer for the movement on goods. So I find all these links very appropriate and very applicable. So that, and to me, it's science that it's in touch with today's problem that are going to be useful for ARB to be aware of of that. So that's basically where the setting of the problem, where we are, the background that we have. And my colleague Mark will indeed describe the methodology that we use to solve this problem in front of us, and then we'll proceed with some of the results that we obtain. Mark?
Okay, well, thanks, Ronald, for the overview. Can everyone hear me? Okay, so yes, I'm going to talk about, start with the biomass resources that we have in California. And many of you may know, we have a variety of resources in California that could be used to, in some ways, to produce power or fuels, right? So we have this geographical distribution of forests in the northern part, especially of the state, that has some waste that can be utilized at some point. There's some thinning operations to minimize the risk of forest fires. So there's a lot of ways that can be used that hasn't been used, or there's some prescribed burning that is being conducted, but so then we are having some emissions related to that, but not utilizing the potential energy from burning that thing. So this is one of the resources that we could use. In the Central Valley, California is the biggest producers of produce in the United States, so we have a lot of waste there that also could be used. And plus, we are, I think, the most populous state in the US as well. So we have Los Angeles, especially San Francisco areas that have a lot of waste that are taken to landfills. So there's the potential of biogas from those facilities together with the wastewater treatment plants. So there's potential for that. The current capacity it fluctuates, but it's on the order of 1,200 megawatts. And there's a potential of additional 4,000 megawatts if all the resources could be used. And again, some of the estimates are from the California Biomass Collaborative, and there are fluctuations in the potentials after several revisions, but the order, as you'll see, is on the order of 4 gigawatts of power. Okay. So having this overall picture, if we look at only solid residue potential, this map shows you two things. It shows you in green per county potential of power if we just use the bioresources to produce power. And then in the blue square shows you the actual locations of the current locations of the solid residue biopower plants. So you can see that the potential is, and the plants are around where the potential is. That's good. And we see that in the northern states, the northern counties have a lot of potential due to the forest residue. If we look at the technologies that are currently in place, it's a big table, so it might be hard to see, but mostly are basically boilers in different configurations. There are boilers, or there are some fluidized bed type of technology, but it's just the biomass that is burned and converted into steam somehow, and then running, or either to produce power or heat. We have that about 40% of the installations actually have both combined heat and power, so some heat is also utilized. If we look at another resource, we have landfill gas potential, and again, this shows in green the potential per county level. So you can see that Los Angeles County has the highest potential because we have the largest landfills, the highest population, and we have the locations of the landfills there. So in that case, we also have a distribution of technologies that are in use currently, and mostly are whether they are gas turbines or reciprocating engines. Right? In this case, we don't have combined heating and power. There's not a lot of heat demand in landfills, so that it doesn't make economical sense to have that type of facilities. So, and we know that especially in some districts like the South Coast, engines have problems meeting the standards, so they might require future end of pipe treatment for these type of technologies to be utilized there. So these are the current state of technologies. And I'm showing these two sources because if you look at this chart now, this is just showing the potential of power, producing power from the different biomass resources. So in blue, showing the existing facilities in 2011. And again, this is from the California Biomass Collaborative. And it's showing that especially solid fuels have the highest, it produce the highest amount of power, followed by landfill gas installations. And the potential in 2020 shown in red shows the same trends. You have the two main resources are solid fuels and landfill gas. Okay, we have potential for an increase in animal manure use to produce power or some other uses. But yeah, landfill gas and solid fuels dominate. Solid fuels, it can be, there's different sources. So if we break that down into the main components, we have that 3/4 of the resources or more could be from forestry, from forest waste. Okay, this also so if we took all the trees down, we could get more power. So we're not doing that. So this is only assuming the resources that could be recovered sustainably. So there are some riparian zones and high slope forests that the estimates do not account for that type of resource. So having this, the potential for power or the resources to produce power or maybe fuels, then with those potentials, then we can start assessing the emissions. Okay. So, and for that, we go back to the literature. We try to find emission factors for different technologies, and we find that for every technology, there's an emissions range, whether there are some different regulations that limit the emissions of these technologies, and different technologies that are being used in the state. So in the four first, so let me see, use the mouse here. So these four technologies, engines, gas turbines, macro turbines, and fuel cells are typically used for gas applications. We have solid fuel boiler and gasification systems that are for solid fuel. And these are just showing NOx emissions. So of course we are looking at other pollutants. So putting these things in perspective, first of all, well, fuel cells, it's not that they have zero emissions, but they have a small emission factor. The other thing is we look at gas applications. We have, for instance, Air Resources Board emissions limit for 2008 and 2013 for biogas applications. So if you look at the values that we obtained in the literature, they are basically, if you look at the engines or gas turbines or macro turbine generators, they are not meeting the 2013 standards, right? So there would be a need for further emissions controls. So based on this figure, you can see maybe just fuel cells can meet unless there's some additional emission controls. For solid facilities, this is just showing the average emissions factors for all the facilities in the state based on the permit levels. So, and there's the question always like, some of the facilities might emit at a lower level than what they are permitted for, hopefully. But so this is just the values based on the permit levels. Okay. So if we use these values and you can see these ranges that can be from very low to high emissions, and we multiply this by the potential for biopower, then we can estimate a range in emissions, potential emissions that could be generated from biopower. Okay, so again, you can see, of course, since the solid fuels have the highest potential, have also the highest potential for emissions. And if we look at the highest bound in emissions, we can see that solid fuel producing biopower could add more than 200 tons of NOx per day. So again, putting these things in perspective, there are two things. First, the inventory that we were using from EPA estimates on the order of 10 tons of NOx per day, and this seems to be on the lower side. We believe that there are many facilities that are not in the inventory, so it's good that we also reassessing the emissions of the current installations. The other thing is that we have, based on ARB's inventories, that by 2012, we had on the order of 2,100 tons per day. So if we add more than 200 tons of NOx from biopower alone, that could be on the order of a 10% increase in NOx emissions in state. Right? So again, this is just showing the potential lower and upper bound. So this is just to bound the problem that we are studying. And so the previous, let me go back to so this is just showing just the facility, right? Just once you have all the solid, all the waste, all the biomass in the place, you're just converting into power. But of course, most of biomass has to be collected, transported, and taken to the facility, right? So we assume for this project that, let's say, municipal solid waste is being collected anyways, it's being transported anyway, so we would not add additional emissions if we were going to use that municipal solid waste to produce biopower. But for forest waste, for instance, there's still a lot of waste that is not being collected. So the collection and transport of solid waste from forest residue, that we account as well. So we add those emissions. And then, of course, we have the information. You can see here the location of the freeways, the major freeways, and the location of the installation. So we have this information in order to allocate spatially the emissions from collection and transport. Then we are not only looking at the direct emission from biopower and the collection of biomass, but also we want to analyze the emissions on the full cycle of the fuel production or the power production. So we use the California grid model that ARB also uses to calculate the carbon intensity of the low carbon fuel standard pathways. Okay, so we used, to be consistent, we use that as well. Now for this study then, we consider different scenarios, and there are three major groups. Okay, so we have the first group that is looking at just increasing the capacity using the conventional technology, so using either boilers or gas turbines and engines, okay, under different scenarios. So, of course, we run the case with current capacity. Then there's the Senate Bill 1122 that establishes some goals of installing some biopower facilities. So we accounted for that. Then we have the Governor Brown's Clean Energy Plan, and that's kind of a very generic program that is aiming to install 20 gigawatt of power from renewable power. And for this, as Professor Dalto said, it's not that there's a mandate for having biopower from biomass in this plan, but what we've seen typically that is about 20% of the renewables is generally met by biomass. So we assume this kind of percentage to estimate the potential. And then we went to estimate the effects of the maximal technical potential, so that includes some issues with sustainability and so on, okay? So then having the maximum technical potential, then we then looked at a second type of scenarios where we applied some technological upgrades, and I'm gonna talk a little bit in a couple of slides. But basically changing some boilers to new generation gasification systems and changing engines with, let's say, fuel cells and see what's the effect. And finally, we looked at a possibility of, instead of producing biopower, that is the major usage of biomass in the state, let's convert this into some sort of natural gas. And one of the things that we talked about with some folks here at ARB is that we do not include any economic assessment of this. So especially in the last group of producing renewable synthetic natural gas from biomass, still, especially in the US, there's not a lot of, there are no commercial applications yet. There's some applications in Europe that I'm gonna mention. But so yeah, there's not an economic component in this assessment. So if you look at the increasing capacity with conventional technology, as you see, the first option is to follow the goals of the Senate Bill 1122. And so it just calls for an increase in about 400 to 600 megawatts in biopower. Okay, so if we assume the goals of Governor Brown's plan, then we can see that that we would increase the power from biomass resources. But using our methodology, we are almost capping the potential of biomass from landfill gas, or the biopower from landfill gas. Okay, so but if we look at the total maximum technical potential, we would see that we would produce on the order of almost 5 megawatts of power, and this is also in following some estimates by the California Biomass Collaborative. Now, as I said, we consider some technological upgrades, and for solid biomass, we consider the case of going from boilers to just next generation gasification system to produce still power. And based on emission factors in the literature, we could achieve NOx reductions on the order of 97% and PM on the order of 88%. And because of efficiency gains, you could also reduce from just the facility 28% emissions of CO2. Again, and going from biogas running on engines, using the biogas for fuel cells, again, we could achieve substantial emissions reductions in NOx and PM, and also due to efficiency gains, we could achieve reductions in CO2. So computing all these emission factors and also considering the full fuel cycle, we come up with this graph. And this is I know there's a lot of colors and bars, so I will try to walk you through this. So this graph is comparing just the current case with the maximum potential case and just the technology upgrades, okay? And then this is showing in green. In green it says conversion, so this is just a direct emission from the conversion facility. So basically, for the current technology, is just burning the biomass or the biogas in an engine or in a boiler. Then we consider collection and transport. So you can see that the small red bar for solid biomass. Okay. And then we consider also emissions from feedstocks, and that refers to the emissions related to the production of diesel for the collection equipment for forest residue, or the emission from electricity generation that is required for a processing plant or a biopower plant. And then finally, we have the savings. And so these are the emissions saved. And in this case, all the scenarios are producing power in a way, right? So since we are producing power from biomass, we are saving some emissions from the power generation in the state of California. So then, of course, if you compare the current case versus the maximum potential, we have an increase in emissions because we have more power. Okay. Now, if you compare the maximum potential with having technological upgrades, then we could see at least substantial improvements in both NOx and PM emissions. Okay, and also we can have some improvement in CO2 because of the increase in efficiency. So we still have the same resources used, but we have an improvement in efficiency. So looking at the net effect, right? So if you add all these components, then we can see the net effect at the fuel cycle. Okay, so then comparing the maximum potential with the technology upgrades, then you can see that actually you could have overall a reduction in PM and NOx that could be beneficial for a state. Of course, I'm going just one step backwards though. One thing to keep in mind is that the savings typically do not occur around the same area where you have the direct emissions from the conversion, right? So you have the facility that is producing biopower, but instead the power production is occurring somewhere else, and the emission from all the feedstocks occur somewhere else. So you bring in natural gas from the Gulf, or even you can import some electricity from out of state and things like that. So it's not a direct addition, but this gives you at least a net effect of these scenarios. Okay. So now we go to the third group of scenarios, and then again for biogas. So we're going to, instead of produce biopower, we're going to produce biofuel. And then for biogas, we have already some examples of producing compressed natural gas just by simply cleaning the biogas from landfill or wastewater treatment plants. If we were going to use all the potential in state, we could produce up to 2.4 million gasoline gallon equivalents. Okay. There's a lot of potential. And for biomass, and for these, there are already applications, so it's not too far technologically. For biomass, if we consider the route of producing renewable synthetic natural gas, so basically you gasify the biomass, produce some mixture of CO, CO2, and hydrogen, and there's some processes. So this picture in the bottom shows you a technology developed in the Netherlands, just gasifying the biomass and producing a stream that is rich in methane, so you produce a methane-rich gas. So if we were going to use all the solid residue in the state that could be used, it could be a potential of up to 6.5 million gallons equivalent of gasoline. Or instead of producing a methane-rich stream, we could produce ethanol following a similar process. So it seems that from the literature we've seen that actually the potential for producing ethanol is from the same feedstock is lower than producing compressed natural gas. So actually that's an interesting area. Okay, but if you just look at the potential for compressed natural gas, if you add the two from biogas and biomass, that could give you a substantial amount of gasoline equivalent that on the order of like 13–14% of all gasoline in state. So that's substantial. Okay. So for renewable synthetic natural gas, we consider the resources that are available, the type of the carbon content for the different resources that are in state. There are some resources for that. And based on some analysis by the pilot plant in the Netherlands, they propose some efficiencies of carbon conversion. So we can use some of the efficiency and the values of carbon content so we can come up with the estimate that I showed before of total methane production. So again, we get to this point where, okay, having all these parameters, we can then estimate the emissions in the full cycle, right? And here I'm showing the maximum potential that I showed before for biopower. So the first one on top shows the power production. Then the next two cases where it says compressed natural gas for vehicles, or we have compressed natural gas just to inject it to the pipeline. And then finally, also producing ethanol from solid biomass. We're going to have ethanol production from biogas here. So one thing, first of all, since for both, for the production of compressed natural gas, now we have much lower emissions from the conversion step because we're not combusting, we're gasifying it, but we are recovering the gas, cleaning up. So we don't have a lot of criteria pollutant emissions from production of compressed natural gas from biomass. We have a lot more power requirements. That's why you see these increased blue bars here, because for the compression and cleaning up of the natural gas, we need a lot of power. So that adds to the emissions and the energy requirements. So we account for that as well. And then we have the savings. Okay, and in this case, it's a little bit trickier than in the previous graph because in this case, we are saving different things, okay? So as I said before, in the maximum potential case here at top, we are substituting biomass to produce biopower to substitute for power in state. In the second case, we are substituting some gasoline with the compressed natural gas. So we are going to use the gasoline for vehicles. So we have the emissions from vehicles, we have the emissions from the gasoline production, and that can be saved. So, and as I said, the potential is on the order of 13–14% of vehicles that could be fueled with compressed natural gas. So that's accounted. In the third case, where we are just substituting the CNG from biomass, we are changing that with pipeline natural gas. So in that case, we are not substituting emission from vehicles and gasoline production. We are just substituting the emission from natural gas production and transmission in the California natural gas system. So we are, again, you see that the purple bars are different. Right? And finally, we have the ethanol production, and the ethanol production instead would substitute the ethanol that comes from the Midwest that is used for blending in the reformulated California gasoline. Okay. So that then gives you different net emissions, right? So if we look at the full fuel cycle, then we can see that in terms of greenhouse gases, we have benefits if we use that compressed natural gas for vehicles with respect to any other option. Okay. Okay. Well, and for criteria pollutants as well, we have that CNG for vehicles is probably the best option among these shown in the graph. Okay, so and as I said then later, so we have all these emissions. Now we want to do the air quality modeling that Professor Dabdo is going to talk about. But so we have these emissions, and we have to allocate them in state. So it's hard to see, but there are some dots here that show the facilities, conversion facilities in the state. We have the emissions from collection and transport, and then we are assuming that we are going to project all these air quality impacts in the year 2020, where we could assume that there's some better penetration of these biopower and biofuels. Okay. So we add these emissions, and then we add these emissions to the air quality model, and we are simulating 2 weeks of a typical air quality in California, one episode in the summer, one episode in the winter. So in the summer we have high ozone and high particulate matter, which is shown here in the plots. So on the left we have ozone, typical high concentrations in the Central Valley and the South Coast. We have PM, especially peaking in the Central Valley, also at the ports of LA. Right, so we use this community multi-scale air quality model, CMAQ model, and we use some baseline emissions that are projected to the year 2020. And that's where the air quality impacts are going to be based on. And then we use some meteorological fields produced with this weather research forecast model. Okay, so with all this, then we can start adding the emissions from all these scenarios that you've seen, and then determine the impacts. Okay, so now Professor Dabdo is going to come and continue the discussion.
So let's look at some results. After all that methodology, what are some of the output and the results that we came across? And there are several results that I wanted to share with you. But this is the first result. This is going one step back. This is, let's take all the biopower that we have generated, which is about 1.2 gigawatt, and let's remove it. What would that do to the maximum 1 hour ozone concentration? So this is an interesting question, and if you look at that, all the computer simulations indicate that it will decrease it in some places, in some hotspots, here around Bakersfield and whatnot, and this will decrease it for about 6 ppb of ozone. So if we decrease that energy that is coming from biopower, and we do replace it among all the other power plants, we see that that is the case. So this is a good place to start. But let's actually take it the other way and say, okay, so we were at 12, so we went to 0 as a first step, and now we are going to go and do the simulations for going from the 1.2 gigawatt to the 4.6 gigawatt potential that we were talking about. And we are going now to look at what the impact of this is in ozone. So if we add more using current technology, and we got questions, we're getting some questions in from the web viewers, and we're going to answer some of them as they come. So this question came from Alicio Viejo, California, and this was the first question. The question, it has a two-part question, was what type of technology was this, some of the simulations, and there are new, more recent emission control technology that you consider. So we have both. This one in particular is using the current industrial boilers and whatnot. So this is what is called the maximum biopower that Mark showed here. This is one of the ways to do biomass. And it's that one over there. It's not the only way, but what we are very quickly discovering is that maybe that's not the optimum way to do it as far as ozone is concerned, nor as far as particles is concerned. So this is the sort of getting the biomass to industrial boilers to generate biopower. And then you say, well, maybe that's a summer thing. Let's look at a winter. How does that differ in the winter? Well, if we look at the winter time, now things look better for ozone. Now you see that ozone actually decrease. And yeah.
I'm sorry.
And even after the Q&A, I'll be here to help. So.
I was interrupting.
Thank you. So this is the impact of adding these 3 gigawatts using basically industrial boiler in the winter. It is somewhat decreases in ozone. But if you look at PM, this is not as helpful before. So what this is saying, in other words, is that if we are, and on top of that, ozone is not a problem in the winter time. We have a particular problem, but it's not such a big thing in the San Joaquin Valley, for instance, ozone during the winter time. So we have this one path to use biomass and biogas. And, some of the people might be asking, are these particulate matters going, are they mostly primary? Are they secondary in nature? What is the origin of this? And what we see is that we have, most of these are in the secondary nature. So all this is basically the NOx emissions that follow the typical NO to NO2 to nitric acid path of oxidation that combine with ammonium to form ammonium nitrate, and this is what these particles come from. But again, this is either winter or summer of this one, what we call the maximum biopower. But now we come to the second part of the question that we got via the web from Alicio Viejo, and the question was, have you done an assessment with the most recent emission control technology? Indeed, and these are the results. Just to remind you, if I can go back a few slides, this is, so what we call the technology upgrade case, and that is replacing the boilers to use next generation gasification and the IC engine with fuel cells. So this is what we call this the effect of technology upgrade. So once you have made a technology upgrade and you use these resources for the same amount, 4.6 gigawatt, things look a lot better. Things look a lot better. So what we are seeing is that we have the same amount of energy and two different paths. And we are seeing that the numbers change quite a bit. So what this is telling us so far is that the path that we get to the number 4.6, it's important that we better, choose carefully. Let's examine another possibility of using these resources. So instead of generating power with older or newer technology, let's examine this case in which we are not generating biopower. So even we take away all that 1.2 megawatts of power, and we use that resource for fuel in what we call the maximum CNG. So that means we are going to use that resource for fuel of vehicles. Okay, this is a very interesting scenario to test. And what we see is that in most of the state, there are improvements in ozone concentration. This was a surprising fact, and this, it doesn't happen everywhere. There are some places that the NOx to VOC are just not helping, but by far the majority of the place, they seems to be, sort of on the bluish color, helping as far as the ozone is concerned. So that is a surprising finding. And by digging a little bit more into this, we found that our collaborators in places like Europe, they are indeed moving towards this part. This is a plant that was made in the Netherlands. It's a pilot plant, but there are some in Sweden and other in Austria that are generating fuel-grade CNG out of biomass and bioresources, following something along this line. So in the event of time, let me share with you the 5 points that I want you to take in summary form. Basically, what this project have done is taken a look at the biomass and biogas resources. We have potentially 4.6 gigawatts. We are currently using 1 point something gigawatts right now. And how to go from that 1 to the 4.6, there are different paths that we can take. Some paths are business as usual, using the boiler. Some paths are better technology. Some path is synthetic CNG and things like that. And the results that you take to get there, it's the same resource, but different path in the way that you choose the technology that you're going to use. What is your final product? Is it ethanol? Is it CNG? Is it going to be power that to use the resource? And what are the emissions control associated with the technology that you're going to have? These paths have very different impact as far as air quality is concerned. So that's the summary, and that was based on this methodology that perhaps was a complex methodology combining a lot of computational modeling techniques. The bottom line, the result is that if you are, what all the simulations indicate, that if you are interested in emissions of criteria pollutant, if that is your most important metric, then the technology upgrades, like the viewer from Alicia Viejo sort of asked about, actually it is the path that will give you the lowest net emissions for criteria pollutants. Well, you might say, I'm interested in the lowest emissions of greenhouse gases, and that is by far the top priority. Well, if that's the top priority, then we have a slightly different path that will be optimum for that, and that is these scenarios that we use this biomass to generate natural gas for vehicles. Very surprising. Some of our collaborating scientists or co-scientists in Europe are going that way. We have not seen a lot of that in California, so maybe this project starts that conversation to happen. And finally, the issue, if you say, well, you know, it's not emissions and it's not only GHG, for me, it's the air quality and GHG. It's not the emission, it's ozone, it's PM. Well, if you look at that, then this biomass CNG for vehicles path, it's still the one that gets you there best. One of my favorite Spanish painter, Pablo Ruiz Picasso, he said, I hate computers. They only provide answers. I think that computers have changed since Pablo Ruiz's time, and they have gotten a little bit more sophisticated. And I think that now, and I hope that he will be happier now, because this is one of the cases that computers are providing questions. And these are some of the questions that, and by all means, we did not answer all the questions. We're just so fortunate to be part of this study, to begin to touch the base of all this very exciting stuff. So some of the questions that we have is, how does that imply, you know, to apply for, you know, the low carbon fuel standard? And we had some discussions this morning with ARB scientists, or how about alternatives? Instead of creating synthetic natural gas, creating hydrogen or isobutanol. And there's the evidence why we want to do that. And we have not studied any of that, or use that instead of CNG for vehicles, use that for sustainable freight transport in some of the ports of California, or, you know, look at in a different way the solid waste recycling. This is the related to AB 341. That how does that impact all this work? These are still some questions that we have. But the one-line summary is that, you know, it seems that our governor and the people of California say we are going to use renewables and we're going to use them more and more. What we are saying is that the path to get there, it's going to be very different from the air quality point of view, and some are more optimal than others. So I really want to thank our program manager, Ralph Proper. He did a superb job to help the science in the project, to manage all and to have us here today. We really are grateful for that, and really thank you to you for your attention.
Well, thank you. It's always a pleasure to be such working with you guys. You didn't need too much direction. Let's start with a question from the audience, and then we'll go we'll alternate with the ones we received online.
Good afternoon. My name is Rick Moore. I work with a company called Edgar & Associates. I've got a question about your making CNG out of all the solid fuel. And wondering, you had 2.4 million GGEs from biogas, 6.5 from biomass. When you looked at that scenario compared to, you know, the other scenario where this was an improvement, did you differentiate between those two pathways to look at the benefit of going with one pathway or the other?
So, sorry, I was distracted with this, but you mentioned that whether to consider just using biogas to compress natural gas and biomass to use
Yeah,
for biopower or something?
I'm assuming you used the blend that you presented here in your analysis. So I was
Yeah.
just wondering if you had something to say about the comparison between these two pathways.
That's a good point. No, yeah, so I guess that we just looked at a small number of scenarios. So yeah, we consider all the resources to either use for compressed natural gas or for biopower. I mean, we did disaggregate between biogas and biomass. I don't know if you can see it well. It's kind of small, right? But so it's still, on average, it's pretty much, it follows the same trend, basically. That the best reductions are achieved both using biogas and solid biomass to produce CNG. If you look at the two, so if you see here, so there's biogas here and biomass. So if you compare biomass here for vehicles with, let's say, biomass here, so there's always, it just follows the same trend. I mean, maybe the numbers, the specific of the numbers change a little bit, but you get the best benefits of converting both biogas and biomass to CNG. And the reason why is that for vehicles specifically, they're producing gasoline and using gasoline vehicles is really pollutant and carbon intensive, especially the production of gasoline. So that's why you see that whatever you do, if you convert anything to fuel, that's going to be the best option based on this analysis.
And you know, for our exercise, we went all the way there just to maximize. In reality, of course, that will not be the case. I just wanted to clarify that.
And again, that doesn't include the economic aspects. So even though you can see that here, that maybe ethanol is not as environmentally good, it's not as good as making CNG, but there's probably a need for either to meet the low carbon fuel standards or to use ethanol for like California gasoline blending. Maybe the small benefits, the environmental benefits that you get from producing CNG, of course, might not compensate the investment that you would need to do to produce just ethanol.
Which also bring the point that you know, some of our web viewers asked from La Cañada, California, and they, you know, one of the issues was, you know, have you done any economics issues, or looking about the selling of the price of either the biogas or the liquid fuels and all this economic and marketing, and we have not done economic analysis. This we discussed it with ARB scientists and staff in this morning. We, as a first step, we're concentrating on air pollutants and greenhouse gases, but no economic analysis.
I have about a dozen questions on the internet. They're still coming in. Why don't we take a question on the internet and then we'll see the audience and we'll alternate?
We just did the internet, so maybe now it's the audience time.
Okay,
Yeah.
Audience next. Right here. Yeah.
Someone had it.
I just had a question for the comparison of the graphs. You're comparing ozone with particulate matter. How does that work? It was a bunch of slides, like 31, 32.
Yes, yeah. Yes, I'm glad that you asked that question. So at what we intend here, we're not trying to compare ozone in the left with PM in the right. They are two different criteria pollutants, but what these plots are showing is the subtraction between the two scenarios. In this particular slide, it's the current biopower versus no biopower. So in this particular case, what this is a mathematical simulation of taking the existing biopower and remove that completely. So what the left will be is what happens to the ozone if we do that. and the right will show what happens to the PM 2.5 if we do that. But we're not meant to compare the two of them. So in this particular case, well, you see that the ozone will stay mostly constant in the left with maybe a few hotspot of decreases when you do remove the biopower that exists. And the PM, it's mostly constant throughout, but a lot of decreases in the middle. But there, there's no the ozone and the PM. They're not meant to be. Yeah.
Just a moment. Right. They can't hear you. You have to wait for the mic.
Are you assuming that if the biopower is removed, it will be replaced by some kind of fossil fuel generation?
Yeah,
In this case?
Yeah, so in this case, we are actually replacing the biopower that has been removed with central generation. So the way we did it is that, so we are removing 1,200 megawatts, right? Instead, there's a capacity on the order of 60,000 megawatts. So we increase the emission from central power generation by 1.2 divided by 60. So it's on the order of 2% increase in emissions from central power generation. And you can barely see any impact of those increases, which means that actually central generation in California is pretty clean compared to biopower at least. So we did include the offset of power that all these scenarios include.
Ralph, let me take one question from the internet. This one came from Matt. And Matt is asking about the alternative fate for biomass. And in particular, he was curious if we don't use the biomass resources for energy, biomass or biogas and whatnot, he was curious about, there will be some forest burning, and if we have, accounting for burning all that potential biomass that will not be used for that. And in these simulations, we did not account for emissions of biomass burning. We did not assume that all that biomass will be burned anyway.
Yeah, and there's another question that is basically asking the same from Jay Johnson. But so that's true. So especially for forest residue, so there's some thinning operations that are conducted. So there's some prescribed burning, and we did not remove those emissions. And that's probably some additional research that we would be happy to do. There are things that make the analysis complicated because prescribed burning are conducted generally in episode. Typically, you want to do this prescribed burning when there's not to minimize the air quality impact. So you typically do these when there's low ozone formation or low PM formation. So whereas biopower, we assume that is operated constantly to maximize the power, right? So it's a difficult comparison, but we did look, and we didn't present the results here, but we did look at the emissions, at just the emissions, the net emissions, and we do see that there's a benefit of using those resources instead of to produce power or fuels rather than just burning them without obtaining any power. So there is a benefit of using biopower.
I'm glad you used my name is Valchanko from SMUD. I'm glad you use next generation gasification for your future technology. Now I have a question. You said that the conversion of biomass to CNG for vehicles would achieve the lowest emission of greenhouse gas. Let's assume if you use all the biomass, whether it's coming from the low moisture biomass for biogas production and the low moisture for thermal gasification, what will be the greenhouse gas or the emissions if you convert everything for pipeline quality gas for combined cycle power plant use?
That's a good question, and I guess we'd have to compute it. So yeah, we haven't got that specific scenario. So
What's your net CO2 if you convert everything to biopower and fuel? Which is better, fuel or biopower?
yeah. So you mean the net or just the conversion, right? Not the savings.
What's your net CO2? I'm seeing your net CO2 is.
So it's maybe that statement is too simplistic. So they are comparing CNG for vehicles and just enhanced biopower. If you compare these two, they are not too far away. Just CNG is slightly, you obtain slightly higher reductions, so lower emissions, but they are not too far apart. So, but and so that enhanced technology, right? The emission factor for that enhanced technology is a lot closer to combined cycle natural gas plant. So that additional reduction in emissions for a combined cycle plant that could be on the order of, right, roughly comparable at least to the CNG case for vehicles. So there's not a huge difference, the point is. So we didn't look at the combined cycle natural gas plant. Yeah, it's not in the report, but I'm just now again, a conjecture here, but I would say that they could be maybe comparable. And there's a case that we could study. The one thing and one maybe reason why we didn't go there is that, so we did look at the case of piping natural gas, right? And a combined cycle plant is going to take that natural gas coming from the pipeline anyways. Right? It doesn't matter where the natural gas comes from, it's going to come from the grid. And there are some other applications like residential natural gas burning that are going to use the same pipeline gas. So that's why you cannot, or you could, I don't know, we assume that you could not, you wouldn't have a plan that would feed directly into a combined cycle natural gas plant, but we could analyze that option.
And by the way, for our internet viewers, this was the discussion based on slide 26. So I get the cue that we have to answer one internet question, and this is a good one because this question, this is from Hannah Villota. It says, are you aware of major problems with the contamination of the so-called urban wood fuel? Very, very good question, very insightful question. And indeed, this is an issue that we look at in a completely different project by coincidence in collaboration of Professor Don Edwards. What we have found is that there is this paint that was using leaded paint in a lot of our houses are still around, and some of these urban wood fuel is still leaded paint. And what we saw is that the lead is helped to escape back to the atmosphere if you have a contaminated atmosphere. So if you have the same painted lead bin of wood in a clean environment, it is going to get the lead out at as much as lower pace than when you have the same beam of leaded paint, and then you have ozone, and it goes the oxidants, and it pushes the lead out to the atmosphere. And if you have NOx, it also does that. And if you have a combination of NOx and ozone, so this is one of those spiraling situations that the more polluted you have, it will bring yet another pollutant from all the historical houses that might still be around throughout California. And we have sort of quantified very briefly some of what that is. In this particular case, we did not use urban wood as fuel. We concentrated the elephant in the room. We call it. It was the forest. So that is the so-called urban wood fuel contamination. It did not play a role into into that.
Well, let me clarify. I mean, we did assume like part of the municipal solid waste and urban waste for the potential of biopower, but we did not look into the
Into
heavy
the levy.
metals or we just focused on criteria pollutants.
Quick question and comment. Mark, I think you said 11% of the CNG the CNG that you can make with this could fuel 11% of vehicles. Is that in reference to, are you saying 11% of gasoline gallons equivalent or 11% of the CNG
It's
vehicle?
actually about close to 13% of gasoline demand.
Gasoline demand.
So it's not only light duty, but
so what does that GG compare? How does that compare to the market of how much CNG for vehicles is actually used?
You mean how many vehicles are currently using CNG, or?
No, how much CNG you could make versus how much CNG would actually be consumed, say, in a given year by the CNG vehicle market currently?
Well, I mean, in the case, we're just assuming that if we produce all the CNG is going to be used. So it's kind of a simplistic and maybe it's a bounding scenario, right?
Okay.
So, I mean, currently, I think instead we have Linda Lee here can give you more information on that, but we have another project on the CNG potential for vehicles, and I mean, there are like maybe 10,000 vehicles total in state.
Okay.
So, and then, of course, we could feed a lot more vehicles with this CNG than what there are.
And then a quick comment, when you do look at, if you do end up looking at the hydrogen, one of the policy drivers that will be important there is SB 1505, which sets minimum requirements on hydrogen production in terms of renewable energy that's used, GHG reductions, pollutant or criteria pollutant emissions, and toxic emissions. So that would be really impactful in your policy drivers.
Want to take one from the internet?
There's just one, I guess, comment or question, but it's a very valid point that Steve Smallcombe says, what about the use of pyrolysis and lower temperature gasification to produce syngas for electricity and biochar that can be used to sequester carbon? And yeah, that seems like a great idea. It's just we just had a limited number of scenarios, and that could be some additional research that we could conduct. We had some discussion in the morning also talking about the issues of whether we want to use a lot of the solid waste to produce CNG, or we can do more digestion to have some more composting that can be used also as a byproduct. And it seemed to be a push, or at least a demand for that. So again, we didn't look at that option yet, but yeah, there are many other options that we would like to investigate. But yeah, there was one last one, I think from Steven Hernandez. I think we didn't address this, but he's also touching on one on the potential of landfill gases, and there are regulations that are AB 341, right, that are talking about diverting 75% of the commercial waste from landfills, right? So that would reduce the waste that would go to landfill, so that would reduce the potential for biogas production. That could also reduce the leakage of methane from landfills as well, so there could be a trade-off there. And there's an infrastructure requirement for all the recycling too that has to be evaluated. So we talked with AIB too that we would be very happy to research on this, but for this study, we did not account for the diversion of waste. There's a lot of waste in place too, which contribute to the formation of landfill gas as well. So even though there would be a lot, if this 75% is achieved, there still would be a lot of waste in place that would be producing biogas for many years, and that also should be accounted for. But yeah, so in short, we didn't account for this diversion in these scenarios.
And we have a question from Brent Kraushar. This also came from the web, and it was related to to explain a little bit more how these reductions come into play. So I'm looking at slide 35 for those who are joining us in the web. And in this case, for example, we have the difference in ozone and the difference in PM 2.5 at the scenario in which we took all the biopower. So what does that mean in terms of emissions? We have three main points that are going to be the ones that create those differences. Number one, when you reduce the current biopower, immediately you reduce the biopower emissions. To generate that power, you have to emit something. So that's one thing that plays into a role of this thing. The other thing, by reducing these and creating CNG for vehicles, then you are also reducing the VOCs emissions that are associated with cars. You still have NOx a little bit, but if you have a car with gasoline and a car with CNG, so you have that second source of emission. And the third that comes to mind immediately, that where do these things originate? It's in this particular case, which is current biopower versus CNG for vehicles, is in the petroleum marketing. If you have more cars using this CNG, there is the whole generation of that fuel, the whole distribution of that fuel and whatnot might also play a big role, and that is at the end of the day, those are the emissions that are perturbed that create this graph.
Question?
Oh. We got this one. Okay. Oh.
So looking at what you just were pointing at on the slide, in Southern California, first of all, am I looking at the maximum CNG situation or the current biopower situation when I'm looking at your slide?
This slide in particular?
Yes.
Yeah, so this slide, it's the difference between two cases.
Okay.
The case that we call current biopower, it's,
That's
today.
now.
That's now.
Yes.
That's now. And the other case, the scenario that we're subtracting is the simulation that say, you know what, instead of generating that 1.2 gigawatt of power, we're not going to use that resource to generate power. So we're going to remove it, and we are going to generate CNG and no power, zero power, and we're just using that instead of for energy, we're going to use it for transportation.
Okay, so in that scenario, you put more gas in cars.
Yes.
And in Southern California, you have higher ozone levels, is that correct?
If we do that, it depends. If you have, if you look at, in these places, you see a reduction. You see a reduction. In these places, you see a slight increase. So depending exactly where you are, you might see, and that is because the NOx to VOC ratio that some places have, or percent, it's going to determine whether the basically NOx that you're perturbing is going to go up or down. But in general, I would agree with your statement that for most of the state, except for those two hotspots, you will see a little reduction if you take the bio power production as we have it now. Not with these better technologies, but just basically the industrial boiler type of thing.
No, so what's happening here is that actually NOx, for this scenario, we assume NOx emissions are at the same level. We just reduce VOC emissions from vehicles, both evaporative and exhaust emissions. Then we have less emissions of VOCs from marketing petroleum. And then we have a reduction in NOx from the biopower facilities. So we are reducing NOx from biopower facilities because we are removing them. And then we have same level of NOx from vehicles, but we have slightly lower VOC emissions from vehicles because we are switching them to CNG.
So to clarify, the NOx is not from the vehicles themselves, but from the biopower plants. The vehicles is mostly VOCs.
So I mean, this is. We've seen this in the past that you would think that you are reducing emissions of like all the pollutants that they should contribute to ozone, right? And you still see some dynamics that seem somewhat not intuitive, right? But because of the levels of NOx emissions that are in the South Coast especially, we can see these kind of strange dynamics of increasing ozone while we try to decrease slightly the NOx emissions.
We'll go to the next question here.
Rick Moore with Edgar and Associates. I did want to make a quick comment on the urban wood waste. I think there's currently about 1.5 million tons that are burned to make biomass energy currently, and there's a couple million more tons is likely to come available with the mandatory commercial recycling. And so I think that the lead paint issues, they've been known for many, many years. I think they've got programs in place to manage the lead paint concerns. I didn't want lead paint contamination to be the only thing that gets said about urban wood waste. You know, it's generated where the people live too, so that helps. But I also had a question about slide 16. I was wondering if you could show that. The lines that you've superimposed with the regulatory limits on different emission concentrations, I guess, is this kind of an average emission factor, or is this for NOx or something specific?
This is just for NOx, yeah.
Just for NOx, okay.
Yeah, so ARB has these emission standards. ARB has these emission standards for distributed generators, so they are typically small facilities, and so they had these limits in 2008, and by 2013 they will be decreased to that are the same for any other fossil fuel based generator. So and they are low, but those are just for gas installations.
But given the current state of the technology, the engines are really not going to cut it. It's going to be pretty hard to permit an engine.
Yeah, but and then so there's also and probably some people in the room that know more about this. But then so there are installations that can be that can go through the route of permitting rather than going depending on the total emissions levels. If the facility has a certain size, can get a permit from the district that might not be as strict as the ARB limits. That's not for the South Coast. Pretty much they have the same limits, but for other districts they have more relaxed standards at the permit level. So then in some regions, even though those emission factors are high based on these limits, they could still be operated.
Yeah, that's a good point, and it depends on the size of the unit. If it's a bigger, then you need the permit from the district. If it's a small, you have to have ARB, which is a lot more strict. So, yeah.
A question on your slide 23 and slide 26. In slide 26 first, are you saying that if you do CNG, you don't have net NOx? Slide 26.
Yeah, I think that
No
this-
NOx?
Yeah, what slide 26 is 2. I don't know, maybe that the printed
Why
version
both biomass and biogas? Your NOx is negative.
Yes.
yeah.
So that on a net fuel cycle, that could give you reductions in NOx. That's what it's saying.
And then in
Yeah, but I think that it might be that the printed version only showed the last part.
yeah,
And not,
yeah.
and not the,
oh,
yeah.
You're saying
so-
this part?
Yeah, so in other
no,
words,
this one is showing.
the same happened in 26, that it's a two-part slide. So this is the more detail, and the one that you guys got in the printed version is when you sum the pluses and the minus, this is when you get, which is still slide 26.
yeah.
Yeah, so okay, yeah. So you get the net.
He got the net, that's what I was. Mhm.
Another question. It's a big question, overall question. California has greenhouse gas reduction goal, 80% by 2050 reduction. And in order to decarbonize the carbon fleet, meaning the natural gas-fired power plants, biomass or biogas could be the best substitute to displace natural gas. Question is, in terms of net criteria pollutants and also CO2, will you do an evaluation on the CO2 reduction or the NOx? Or if you did already, what's the NOx or criteria pollutant emission reduction and also the overall CO2? And there is a proposed renewable natural gas standard coming, and there is a bill. And biomass is the best candidate to help displace natural gas.
So let me go by parts. So biomass, and it's a good candidate for either produce biofuels or biopower, as we've seen here, and they have, depending on the technology, you have better benefits or not. But even if we use all of them, biomass is just a small portion of the energy that can. So we're talking about 4 gigawatts of power, whereas the capacity of a state is on the order of 60 gigawatts. So that's only producing about up to 7% of power. So biomass will only be able to help you a little bit with the carbon reductions goals. There's going to be a lot of renewables, non-combusting renewables that are needed. I don't know, storage, like system management, and to achieve further emissions. And I haven't followed the specifics of the scoping plan of AB 32, but they probably have some guidelines. But the goal of 80% reduction does not only include power generation, but all the sources, right? So again, if we use all the biomass for fuel, that gives you 13% of gasoline consumption. If you use for power, that gives you 77% of power by biomass. If you use some part for fuel and some part for biopower, then it gives you a percentage, right? So there's going to be the need for other solutions. And we did a study for the EPA, and this is not probably the time to talk about it, but it's going to be difficult to meet those goals. And we looked at the high penetration of renewables, but these renewables have to be balanced with some other dispatching technologies, then electrification of sectors, and so on. But anyway, so biomass, bottom line, biomass is only going to give you a small. It's going to be a small player. I mean, it's a significant player, but still small compared to the bigger picture of the 80% reductions, 80% reduction in GHG. I don't know if I diverted too much from your question.
Pretty sure.
Yeah, that's good.
Yes. Mm-hmm. Good. We have a question from David Cox, and he is asking to clarify this slide 21, and what. Let's take a look at slide 21. In the two extremes, there is this issue of the current scenario, which is today, which is the one that we talked about even at the very beginning. Let me go to even the one that the first slide that Mark talked about, that we have basically the famous 1.4 gigawatt. That's the current capacity that's in the left side, and then in the right side is the maximum potential. So what this slide is intending to do is trying to put some policy-driven SB 1122 or the governor's clean energy plan to see if they are in harmony with the technical potential that is available, or are they technically infeasible, or are we asking so much? And in particular, so is this slide specific to electricity generation, or transportation fuels are associated? So we're not specific to this slide in particular. It's more specific to electricity generator. What we looked at, and one of the scenarios indicated, is that if we use that resource and instead of doing electricity, doing a little bit of transportation, that could be helpful. So this slide in particular, it's looking at how does the current and maximum potential fit with other ones based on the electricity and other parts of the study. We started to question whether going all to electricity or perhaps not some of them, how does that fit into the picture?
I think that's all the questions we have on the internet then. And if there are no more questions from the audience here, let me just say, it's a very interesting and complex topic, and I really appreciate your elucidating a lot of these choices that we definitely need to consider for the future. We would like people's ideas for any future work that we think should be the focus of research. And beyond that, just thank you very much again for the presentation, and I'm sure we all appreciate it.
Yeah, I wanted to thank the audience. The kind of question, this is the most exciting seminar, and I think that it does get the point that it's a relevant topic. It is something that we all have a lot of questions. And if you look at the literature, there is not a heck of a lot of work done there. And I feel so privileged to have worked with ARB and start getting those computer simulations, start looking at the numbers, looking at some surprises. And we were surprised when we were started to look at those things. It has been really, really exciting, and I really thank you for all the the questions back and forth. That's probably the best compliment to have after a seminar, to have lots of questions, and I really appreciate that. Thank you, guys.
Thank you.
Now, I have to insist, we have interviews, and we need to conduct them.